webinar. At this level, I think you know who I am, Andrea Roncoroni. I am managing and directing the Energy and Commodity Finance Research Center at the SEC Business School. So today it's a pleasure for me to introduce you with Professor Rafal Weron from Wrocław University of Technology in Poland. And here is Rafal. Welcome to Paris. He is going to make a presentation on forecasting electricity load and prices. You all know that Rafal is perhaps the most important worldwide expert in forecasting electricity and load volumes. So he wrote an important book, an important handbook for Wiley on the subject. And now I give the space to him to make this introduction to us. Thanks.
Thanks, Andrea. Thanks all of you for coming, and all of you out there somewhere in the cloud. Okay, so as Andrea said, this will be a talk about forecasting two probably most important processes in electricity markets, meaning electricity loads, sometimes what we refer to as electricity demand, and electricity prices, wholesale prices. Okay. The topic we are going to talk about today is a topic on recently very active. Recently we see a lot of very many publications coming out on this topic. This is something that has also appeared in worldwide competitions. So electricity, we both look at loads as a major process in electricity markets, and prices. The very recent competition that ended in autumn last year, the Global Energy Forecasting Competition 2014, involved 4 tracks: load, price, wind, and solar forecasting. It concerned probabilistic forecasting, and we will talk about it a bit more later on. 2 years earlier, the first global energy forecasting competition, 2012, concerned only loads and winds and only point forecasting. So there's a major difference. There's a major change also, not only in the academic world dealing with electricity markets, but also in the practitioner world. More and more people are aware nowadays that probabilistic forecasting is something we should look at and something we should develop more than what we have done before. So 2 recent review papers. Last year in December, it came out in International Journal of Forecasting, a review on electricity price forecasting. This one on probabilistic electric load forecasting is coming out this year, also in an International Journal of Forecasting. So if you want to have a summary of what's going on in this area research-wise, then these 2 papers are definitely worth recommending. Okay, so if you want to go a bit outside those reviews, then the major outlets for this kind of research, electricity and load forecasting in electricity markets, are the following journals. As you can see from the top 4 are related to engineering sciences, and the first one, the IEEE Transactional Power Systems, is definitely the most popular outlet for publishing this kind of papers. Actually, what I have here in this plot is articles related to electricity price forecasting. If you consider load forecasting, then you won't even see papers in energy economics or energy policy, or well, maybe a few in the journal of forecasting, but definitely the engineering sciences are leading the way here. So this is where you should look for new articles coming out. These are the journals which publish good research in this area. Now, when talking about forecasting, you always have to specify the forecasting horizon. So here, in this talk, I'll talk about 2 forecasting horizons, short-term and mid-term, defined in the following way. The short term was from a few minutes up to a few days ahead. This is the forecasting usually performed when bidding in the day-ahead market. The medium term ranges from a few days to a few months ahead, and this is usually done for balance sheet calculations, risk management, derivatives pricing, and as you see from the further part of the talk, there's an inflow of finance solutions coming in. Reduced form models are definitely brought into energy economics and are used for medium-term forecasting or modeling of these processes, mainly of the price process. The long-term context, I mean, from a few months or actually from a year and beyond, is not touched upon in this lecture. It's a totally different story. I do not personally believe too much in the ability to forecast too well beyond a year or so, and definitely different tools have to be used when considering these kind of long-term horizons. In load forecasting, there's also the very short-term horizon. I didn't put it here, but the very short-term horizon is the next few minutes or so. That's for balancing market operations. You don't see too many papers on electricity price forecasting in this very short-term context, whereas for loads you also see it. I won't be touching too much this subject. However, the methods developed for the short-term forecasting horizon, most of them can be used pretty well for the very short term. Okay, so summing up, we're looking at short-term and medium-term forecasting horizons, ranging from a few minutes or, well, actually an hour or so, up to a few months ahead, let's say a year. This slide comes from my review article on electricity price forecasting. It's one slide which shows you what kind of models you can find in this area, and essentially most of them are also found in load forecasting. So maybe starting from the right, here you have computational intelligence methods. These methods have been very popular and developed mostly in engineering sciences. So if you look in engineering journals, definitely you see computational intelligence methods, in particular neural networks, fuzzy methods, support vector machines. These kind of algorithms or techniques have been used and are constantly being used to forecast electricity loads and also electricity prices. The next column, the statistical methods. These methods are I usually taught at economics or maths departments, and you can observe papers using these kind of methods by the authors who have graduated from such schools. So there's kind of two lines of thought. You have the statistical from economics, math statistics, and you have the neural networks from, let's say, computer science and engineering. The typical members of this group are exponential smoothing, regression, all kinds of regression models, autoregression models, threshold models, heteroscedastic models, and so on. The next column shows you reduced form models, and these are the models that come from finance, and two classes: jump diffusions and Markov-Region switching, mainly introduced for modeling electricity prices. Because of the spikiness of electricity prices, this unexpected and very extreme changes in price level, both of these approaches have been introduced to modeling electricity prices, not so much into modeling loads. The next class, fundamental models. That's a class of models, the version group actually, and some of the models from other classes can be regarded as a mixture or a hybrid of a fundamental model and a time series or a computational intelligence model. These models work out some formulas, relations between some fundamental factors, let's say weather, for instance, weather variables, consumption levels, and so on, and try to combine them into an equilibrium type model where the equilibrium sets the price that you model through these formulas. So it's usually a big set of different equations modeling different aspects of what is going on physically when you are dealing with energy demand and energy prices. The last class, on the very left, multi-agent models. These are models definitely for price modeling and not so much for forecasting. Some of them have been used for forecasting, but there's not that much success. Still, I put it here as for some markets, like the Spanish market, where you do not have too many participants, too many major players, you can try to work out models in this kind of game theoretic models, in the Cournot framework, the supply function equilibrium models, strategic production cost models, and the last class here that fits in is agent-based models. Agent-based models are becoming more and more popular, not that much for forecasting the price or the load on the next day or the next few days. It's more for analyzing the behavior of players in the market. So this overall, you see a summary of what kind of methods techniques you can see in this area. Some of them are more popular, some are less popular, yet all of them are there. Now in the later part of the talk, I will discuss 5 issues that, in my opinion, are things that will be developed or are being developed currently, or will need to be developed more in the near future, that are related to load or price forecasting. So the 5 issues are the modeling and forecasting of the trend season components. This has been to a large extent ignored in the price forecasting literature. Then we talk about probabilistic forecasts, combining forecasts, multivariate models, and finally evaluating forecasts. So all these issues require more attention, and I will go over each of those in the next slides. So first, if you talk about the trend seasonal component of a price process, of the load process, of course they are very different. The load is much more deterministic, much more periodic. It's much easier to model and to forecast. But if you think about the price process, electricity prices, there the trend component is so obvious. There, usually the annual, the weather cycles are there, but they do not necessarily translate to a very seasonal behavior of the prices themselves. Still, the models that are used in the medium term, not so much in the short term, have to rely on such a model for the trend seasonal component. The classical way to do it is to decompose the time series of prices. I will be talking because of prices, because loads, as I said, are much easier to model in the longer term. They're more deterministic. We decompose the time series of prices here, PT, into the long-term trend seasonal component and a short-term seasonal component. The short-term would be usually the weekly component. Anything beyond that would be called the long-term trend seasonal component. So we have these 2 seasonal components in our series, and if we are able to decompose the price series into these 3 parts, so these seasonal components and the remaining variability, or the stochastic component, then we can model the stochastic component in some adequate way and use it for pricing, for risk management, and so on, by adding later on the forecast of these components. As I said, the hourly or weekly, so the daily cycle, the morning peak, the afternoon peak, the off-peak hours at night, these are usually captured by autoregression or dummies. So forecasting of this is rather straightforward. There's nothing really difficult about it. However, annual seasonality, or the longer term seasonal component, is present in the prices, but it's not so obvious. You cannot see. It's not exactly seasonal as you would like to have it. So from year to year, there are big changes in the price levels, even for the same period of the year. This is all due to the different macroeconomic factors like fuel prices, economic growth, also to longer-term weather trends, changes in the system, the physical system, the construction of the system, the number of power plants, the different generation facilities, and so on. However, to show you why this is crucial, let's consider the following example. Take a time series of prices. This is the Nord Pool spot price in between 2012 and 2013. So it's oh, there's a 2 missing here. Actually, it's 2 years of prices here, and you have 3 commonly used long-term system components fitted. The green one is monthly dummy, so you have a constant function over a month period. There's a kind of a step function you observe here. The green one. The black dash dot is a sine function. Again, it's periodic. It's very easy to predict, like the monthly dummies. However, the fit is not so good. And the third one here is the wavelet-based long-term same kind of a trend component that is in the data. As you can see, it deviates at some parts a lot from the sine function, and this makes a big difference. Now, if we remove these trend components from the data, remove also the weekly component, which I'm not showing here, and look at the residuals, and then calibrate or estimate a simple stochastic model to the residuals. That's what we usually do. And this simple model in this case is just a jump diffusion model. So it's a mean reverting process with Poisson jumps. Then, if you fit it to the residuals of the prices after removing the wavelet component, the fit is nice. The obtaining process is nice, and this is something you could expect. I mean, some mean reversion from time to time, you see a jump. This is pretty realistic. Whereas if you do the same for the sine component or the monthly dummies, you observe very different behavior, which is not really a mean reverting process with jumps. So definitely the residuals cannot be modeled by this jump diffusion model, the stochastic model. So you have to be very careful when you compose your series and use different stochastic models for the residual series, the stochastic component. The plots look very much alike because the same random numbers were used to obtain all these 3 plots. These are just sample trajectories of the models estimated after calibrated to the residuals, and these are just sample trajectories. As you can see, only this one gives you a reasonable fit of what's going on in the market. Now, a big question is how to forecast the season component. Now, if you have monthly dummies, if you have sines, then this is a purely periodic function. You just extrapolate it in the future. There's no problem at all. What happens if you have a smoother like a wavelet smoother? Now, the idea we had at some point was to just smooth out the signal. So take the original signal, this is our prices up to some point in time, and then assume, which is a reasonable assumption, that the prices are mean reverting. So assume that 1 year from now, let's say, or 2 years from now, the price will revert to the mean level or the median level here. And all we do is connect the points, either the last price point or the red one is working on spike filtered prices, so there's some variance. You can filter out the most extreme observations to have most of the variability except the most extreme observations. So less variable, there's less variability in the process. You just connect these points by some kind of a, let's say, exponential decay function in this case, and then fit a wavelet smoother to those curves. So the red one is fitted to the prices plus this exponential decay here. The blue one is fitted to the other one, the original to the exponential decay starting at the last spot price. And this can be used, this wavelet fit can be used as your forecast of the season component. Of course, it's not a very good forecast, but still, as we show in this paper, it beats the sine and the monthly dummy methods. We analyzed a bunch of methods, 300 all over, and the wavelet methods are much better than than even with this simple extrapolation of the seasonal component into the future. They are better in terms of predicting the level, the differences between the actual levels later on and the forecasted seasonal components are smaller than for the other methods. At this point, it might be, you might ask a question, why not use forward-looking information? Why not use forward prices? Well, this is not so obvious how to incorporate it. Forward prices include the so-called risk premium. So there's something more in the price. It's not just the forecast of the future spot price. It's there's also some premium added there. It's not obvious how to extract it and how to get the forecast, but you might think of using it. And as far as I remember, Andrea, I've been working on such a model. I don't know if it's published or not yet, but when we met in the Reacher, you had a model like this where you use forward-looking information, forward prices, forward curve to forecast the future spot prices. Okay. At some point, one of students of mine, Michał Zador, asked the question: why do we have to use wavelets? It's a kind of a pretty complicated technique. Maybe use something simpler, simple smoother. And one of the most known smoothers in econometrics or macroeconometrics is the Hodrick-Prescott filter. This is just a method that smooths out an original signal where you have the original as yt, this can be the price process, and the series is tau t, and you minimize the value here, which is a penalty original series and the penalty for the roughness of the smooth series. Okay? Minimizing this, you obtain a smooth function. Interestingly, this smoother, you can see here for different values of the parameter lambda, it can be more smooth. It behaves very much like the wavelet smoother. So this is a simpler method to use instead of the wavelet. This can be done even in X, so it's a very simple technique. And you can extrapolate the forecast in the same way as the wavelet smoother. Interestingly, this table shows an empirical study, a simulation study, where we use some long-term seasonal components from this class, so S5 to S8, those are different wavelets, assign seasonal component, and then estimated different. So we generate trajectories using these seasonal components, added some noise from a mean reverting jump diffusion or Markov regime switching model, and then try to extract the long-term seasonal component that's in the data. It turned out that the Hodrick-Prescott filter in some cases gives us a better fit than the original model. So if you, for instance, in this case, you have a wavelet of 6 levels after 6 levels of decomposition, this should be 0. This is the deviation from the optimal from the true seasonal component. As you can see, that the smallest deviation was obtained by one of the Hodrick-Prescott filters. So it can do even better than the original series. It can do better than the sign combined with an exponential moving average. It is a very general technique, very simple, and can be used in the same way as the wavelet smoother. It's just simpler. Okay. The next point here is for probabilistic forecasts. As I said in the introduction, probabilistic forecasts are forecasts that give you more information than what you are typically used to, meaning a point forecast, just a point estimate of what is the future, the next days, the next weeks, the next month's value of a price or load. So given that nowadays in the smart grid era, the variability of load demand is so high, it becomes a challenge to forecast the loads. The methods that have been used for many, many years are no longer or may no longer be adequate in this case. The extreme variability of electricity prices also questions whether looking just at the point forecast is enough. perhaps we need more information. This more information can be achieved by computing so-called probabilistic forecasts, which are either intervals where with certain probability, let's say 90%, the price process will be tomorrow, next week, or next month, or the whole density of the future price process. They are very useful in practice. I mean, for risk management decision making. I mean, the value-added risk methodology, what is the core technique in risk management, it's essentially an interval forecast. It's a forecast of what is the probability of not exceeding a certain level. That's exactly it. So this is also becoming more and more commonplace in electricity markets, and also this can be observed in the competitions. The Global Energy Forecasting Competition 2012 only considered point forecast. The last year's competition was focused only on probabilistic forecasts. So now the question is how to forecast the next days or the next weeks or the next months, price or load or wind power or solar power, whole distribution of prices in that day. Since I'll be talking a bit more on probabilistic forecast in the next topic, so let's now move on to the third issue, combining forecasts. Combining forecasts is a long forgotten art. For some reason, for many years, people have not used this in electricity markets. I mean, the history goes back to the 1960s and the works of Bates and Granger and Crane and Crotty, which were some of the first papers published on the idea of combining forecasts, meaning that you have a few predictors, a few methods to predict your process, whatever it is, the load or the price. And in the simplest case, you just take the arithmetic average of those predictions. And this has very good properties. It's robust. It has lower variability than any of the individual forecasts. And on average, it's not worse than the individual forecasts. So in the electricity markets, in the demand or transmission congestion forecasting, there are some papers. From time to time, there were papers already in the 1980s, and from time to time, something appears. However, if you look at the electricity price forecasting literature, this is really new. I mean, just the first paper appeared 2 years ago, and there's an inflow of new papers coming in, considering how to model the distribution or the intervals of the future price process. Interestingly, if you look at the electrical engineering literature, there are single papers, and more coming nowadays, where people look at so-called ensemble averaging or committee machines. This is essentially combining forecasts. So you have, like in this paper, Gawolnu, combined real basis function network with 23 inputs and 6 clusters, multi-layer perceptron, to compute daily average on-peak electricity price for New England. So essentially, they have two forecasters. One was a real basis function network, one was a multi-layer perceptron, combined it to yield one price. This is the idea of combining. It seems that forecast combinations in the statistics, econometrics literature, and committee machines in the engineering literature, they kind of evolve independently. It seems the authors are not aware of the developments in both areas. This is something that has to be changed. Apparently, both sides can learn from the developments in the other sector. So what is forecast averaging? In the case of a point forecast, you have a set of predictors. You call them individual forecasts. They can come from different models. They can come from different experts. You may ask experts to predict something. You just take those values, F1 and Fn, assign some weights. In the simplest case, the weight would be 1/n, so every observation would be weighted with the same weight, and then take the weighted sum as your combined forecast. Okay, this is the idea of combining forecasts. So should we combine or not? In this example here, we look at data from Nord Pool region. This is just a calibration period for the individual models, and then the combined forecasts are computed for this rectangular window here. The lower plot shows the errors of the different methods. So all the individual methods are just gray bars. I do not distinguish between the different methods here. And the different symbols like X, star, or square are different combination schemes, different methods to combine forecasts. The simple is just the 1/n, simple arithmetic average. The others use a more sophisticated ways of combining weights. Now, as you can see, generally, the symbols are lower than the bars. If we look at some statistics and compute the mean absolute error, weekly mean absolute error, so you are weighting it by the mean price in the whole week, the lowest values obtained for one of the forecast combination methods, constrained least squares method. The number of the best forecast for a given week, this is for 8 weeks, was the best. The simple, this constrained least squares was the second best. If you look at the mean deviation from the best model in a given week, again, it's these methods, the combination methods are way better than the individual methods that were used to obtain those combined forecasts. So combining in the case of point forecast definitely makes sense. And this has been noted in the load forecasting literature, not so much in the price forecasting. Now the problem is that if we go on to interval forecasting or density forecasting, it's not so trivial. For interval forecast, the above formula doesn't hold, meaning that a linear combination of the alpha quantile, let's say the 90% quantile, is not the 90% quantile of a linear combination of random variables. So we need to develop different techniques to combine interval forecasts. And one of the techniques that we have developed recently is so-called quantile regression averaging. It uses point forecast to produce, combines point forecast to produce an interval forecast. So the idea is here, you have again n predictors, n individual point forecast. Then instead of simple averaging, weighting, you use a quantile regression technique to obtain a quantile, given a quantile, the one that you want for a sample. And this, doing it twice for two different quantiles, let's say for the 5% and the 95%, you get the interval between 5 and 95%, meaning the 90% prediction. So this is a combined interval forecast. Now, the averaging problem is given by the following equation. So on the left-hand side, you have the conditional quantile of the electricity spot price distribution. However, of course, this could be also load, if we have applied the latest to loads. On the right-hand side, you have the different regressors. So those are the different individual forecasts. And W is a vector of parameters for a given quantile. You obtain these weights by minimizing the following function. So there's some penalty. You can think of it as a penalty for exceeding a given level or being below below this level, and this penalty is proportional to the quantile level. So if Q is, let's say, 5%, this will be 5% penalty, this will be 95% penalty. So on one side you have a heavier penalty, on the other you have a lighter penalty. So this is called the pinball function. In the GEFCON 2014 competition, this function was used to evaluate the forecast. You will see it also in one of the later slides. For Q equal on half in the median, this yields the so-called L1 regression. This is just the minimization of this formula, the absolute value, absolute error you can think of. Graphically, quantile regression, instead of just fitting a linear regression line, you find such lines that, for instance, the upper one here, this is the 95% quantile, so that 95% of observations are below this line, 5% are above this line. Okay, this is the lower one, so 5% are below, 95 are above. That's the idea of quantile regression, a technique which is becoming more and more popular in this context in risk management and in forecasting, probabilistic forecasting of electricity prices or loads. Case study here, we have 6 individual point forecast models: autoregression, 12-strong autoregression, and semi-parametric autoregressions, mean diffusion, a neural network, and a factor model. So we have 6 individual predictors, the calibration period for the individual models, the calibration period for the combinations, and then we have forecasts for this period in this rectangle here. And we'll be evaluating it in terms of Christopherson's test for the unconditional and conditional coverage. So we focus on the sequence of exceedances. So if we are in the interval, if the observation falls into the interval, we give a value 1. If it falls outside, we give value 0. And we can check whether the number of ones corresponds to the nominal coverage, meaning, let's say 95% of ones we have in this series, if this is a 95% interval, and if they do not cluster. This is the independence test. So conditional coverage is the unconditional coverage, meaning if we get the nominal coverage right, plus independence, plus not clustering of these observations. And looking here just at the unconditional coverage, just 2 of the individual methods are selected here. The others were even worse. This is the quantile regression average, much better, much closer to nominal value. So this is almost 50%, almost 90%, so nearly a perfect fit. If we look at the width of the interval, it also is the smallest compared to the other individual methods. So this gives you a very nice technique for combining individual forecasts and getting an interval forecast out of it. Looking at Christopherson's test, anything below the solid line is a very good fit. For each individual hour, we look at the observations, and only for the quantile regression averaging, both the unconditional coverage and the conditional coverage, meaning also the clustering, it's not observed, and this method passes for nearly all hours to test. Whereas the individual methods behave very bad, and for most hours it cannot be accepted as a good interval. So this shows you the superiority of this quantile regression average technique over individual methods. The next example here is a case study on loads this time, and in this case we'll be, instead of using like previously 6 different techniques to obtain 6 different forecasts, we will be using so-called sister models. Sister models is a idea developed by Tao Hong from UNC Charlotte, where he takes one big family of models and then fits those models to slightly different data, different calibration windows, different ways of using of the training and validation periods. So the general formula for the model is the following. So maybe on the next slide we'll see it better. And this, for each model which is calibrated to a slightly different calibration, different data, you obtain a different forecast, and this will be called sister forecast. We will be aggregating or combining those sister forecasts. So the model, if you look at in more detail, takes some calendar effects, so month, week, hour dependencies, temperature dependence, and this temperature dependence is a kind of complicated function here, which may depend also on different hours and times of the year. Some recency effect, the lagged temperature, the previous temperature in the previous days taken into account. So this is a huge regression model with many parameters, and now using slightly different data sets for calibration. For instance, only one particular hour, all 24 hours of the day, using a 2-year window or using a 3-year calibration window, we get slightly different models. We use them to obtain the sister forecast, and now what we are going to do, we are going to combine them to obtain forecasts for using this quantile regression averaging technique. This is the data loads from somewhere in the US. This is the data that was actually used in the load forecasting track of the GEFCON 2014 competition. It's freely available on the website. You can also test your techniques against it. And if we look also at some naive benchmarks of obtaining prediction intervals. One of them was just a scenario generation from historical weather data. There was no recency effect, just kind of no luck temperatures taken into account. Another one was quantized were interval from 8 individual forecasts. We had just 8 forecasts, and on them we spent all the percentiles, all the 99 percentiles we looked at. Also, the individual models, or the best individuals selected always a week before in the previous week. So this was also a model selected, one of the 8 sister models that we used, but chosen on a recursive basis week after week. The evaluation forecast was done using 2 functions. One was the pinball loss function. This is the function, as I have mentioned, this is the same function that is used in quantitative regression. This was exactly the measure of error in the GEFCOM 2014 competition. The second measure was the so-called Winkler score or interval score, where you have a penalty like the one here, essentially, for exceeding from the above or below your interval, plus you add some penalty for the interval width. So the wider the interval, of course, the higher the probability of falling into the interval, but you don't want wide intervals. So you prefer narrower intervals, but you add penalty for exceeding them. So that's how you compute this function. Okay, and comparison table. Now the also quantitative regression averaging in terms of all 3 measures. I mean, the pinball function over all 99 percentiles of our distribution, the Winkler score for the 50% interval, and the Winkler score for the 90% interval. This technique is always the best. So again, using completely different data. Previously we used electricity prices, different individual predictors. Now in this case we use electricity loads, 8 sister models from very similar regression models, just calibrated with different data sets, yielding different sets of parameters. Again, we obtain that the interval predictions are best from this technique. So you can think of this quantitative regression averaging as a technique which leverages from point to probabilistic forecast. So it lets you use your techniques that you have developed for years for point forecast of your process, the load or the price or whatever it is, and then combine them to yield the probabilistic forecast. So this technique is a very general technique, and interestingly, I think right now is a conference in California in Riverside, the forecasting symposium, where the methods that the different contestants used in the GEFCON competition will be presented, and 2 out of, I think that the top 2 entries in price forecasting track, one of the top 3 entries in the load forecasting track, they used quantitative regression averaging or a variant of this method to obtain the forecast. So this is a very good technique, not only in terms of academic behavior and publishing papers on it, but also in practical studies, where you actually have a practical task of forecasting loads or prices for the next day. Okay, an extension when, for instance, if you have a large number of predictors, not 6, 8 like we had before, but let's say 50, it may be not optimal to run quantitative regression on all those 50 regressive on all those 50 predictors. It might make sense to use some kind of a dimension reduction technique, like a principal components, to extract the factors, the most important dependencies there, and then combine the factors, not the individual forecast, but the factors estimated from these predictions, again using quantitative regression to obtain the forecast, interval forecast. This technique is developed introduced in this paper coming out this year into International Journal of Forecasting, and as we show there, it makes sense. It is slightly better than a method which does not use this PCA technique to decrease the dimension problem. Okay, multivariate factor models. And I guess we are slowly approaching the end of the presentation. In this slide, I've just introduced a dimensional reduction method like principal components. This is a technique which can be also used when thinking about forecasting point forecasts of prices or loads. A technique that has not been used very often in the past, but again, in the last 5 years, it has gained interest in the energy economics community. Now, what is the idea? We can think of the prices, for instance, or also loads, as vectors. So all daily 24 prices in a given day, or hourly prices for a given day, you can think of them as a vector. And in fact, you should think of them as in such a way, because this is not a time series. These prices in most markets are established in an auction made once a day. At this point in time, let's say 11 a.m., all prices for the next day, for the 24 hours of the next day, are established. So you are thinking of vectors of prices, not of a continuous time series where something changes. So thinking in this way, you can use this information and try to extract some common features of the somehow modify them to obtain just the most important information from the common information that's there, and perhaps use only 3 of them out of 24 after some transformations. So the individual series can be modeled as a linear function of a certain number of principal components. These are FTs are the principal components, and some residuals. And these lambdas are the loads, or sometimes called the loadings. And do not think of them as the electric loads. This is just a loading of a given factor. So you multiply the factor by a given loading to obtain the value of the process. This kind of thinking was very popular in the macroeconometrics. There are many techniques to develop for this, and has been recently applied also in electricity markets. In this example here, we are looking at hourly prices. This is PGM Dominion Hub, and this is the average daily price, the black one. The 24 series are in gray, so they are overlapping. You don't see the individual series, you just see kind of a cloud. And now we want to extract the information out of this vector of 24 prices and find and use this information, just the most important information in those prices, to build a model, an autoregression model, to predict the price, the daily price for the next day. Now, during estimation, we obtain the different loadings of the factors, and as you can see here, the first loading of the first factor, this is the blue curve here, it is more or less a level. You can interpret it as level, because you have this is the night, the off-peak hours, this is the afternoon peak, and more or less this is the level. Then the next 2 loadings of the second and the third factor, the red and the green, make a distinction between the morning peak and the afternoon peak. This is the red factor, and the green one, again a distinction, the late afternoon or evening hours, and some more way to the midday hours. So using a model with 3 factors, we are able to predict next day's prices, and this is kind of this is the average forecasting average forecasting error. This time is the root mean square error over different forecasting horizons, ranging from 1 day to 60 days ahead. And as you can see, it is all normalized by the errors obtained by a simple autoregression, where you fit an autoregressive model to just the black curve, the average daily price. As you can see, in the short term, analyzing independently the 24 hourly series in the short term gives you benefits, because this is being below 1, meaning it's better than the benchmark, the autoregression model for the daily prices. But in the longer term, it can be even worse than the simple autoregression for the daily price. However, if you look at the factor models, you extract the information from those 24 prices, you see that in the short term it's a bit better than the autoregression, but the more we go into the future, I mean, from around 15 to almost, I mean, yeah, 50, 60 days, we are much better than the benchmark. So extracting this information that is hidden in this vector of prices using a factor model, we are able to improve our forecasting accuracy over a longer forecasting horizon. So in the short term, this is not necessarily the best method to use. However, if you look at longer forecasting horizons, using factor models may be beneficial. So, as I said, this is relatively new path of research in the energy economics literature. It has started in the late 2000, okay, let's say roughly 10 years ago, more or less. But more and more papers are coming out using this kind of approach, a multivariate approach to modeling prices. It is not so popular for forecasting loads for some reason. I have not seen too many papers there, but again, this is a technique that may be valuable when you are working with such data. And the fifth point here is how to evaluate the forecasts. As you have seen also in the previous slide, in different papers, even I have used different error measures. This is not maybe the best idea to do. Actually, optimally what we would want to do was to use one or two error measures, the same across different papers, so that the results will be comparable. Also using the same data set. So in part, the competitions like the GEFCON competition, this answers this problem to some extent because the same data set was used by all participants, the same error measures were used to all participants' forecasts. However, if you do research, it is also makes sense to use some measures which are better than those that are worse. So, for instance, especially when analyzing hourly or fine frequent intraday values, especially prices, it makes sense not to use just the mean absolute percentage error, the MAPE, better weigh it by the average price in a certain period. This has been called different names in the literature. One of the names is weighted mean absolute error, where the weighting is not the current, let's say, price for current hour, but the average price in a given day or a given week. Seasonal, more let's say in general, mean absolute scaled error is a measure introduced in this paper here by Hindman and Keller, where you rescaled your error. Again, it's a mean absolute error, but you rescale it not by the current price, which would be pH, that would be MAPE, mean absolute percentage error, not by the average over a week, but by an average of some deviations between the prices. They introduced originally for a lag of 1, M was 1, but in seasonal data, like electricity prices or electricity loads, M could be, for instance, 24, so the lag would be 24. It's like this would be kind of an average differences between the price today and price 24 hours ago. And this gives you a good scale, and you have no problem with values near 0 or negative values. So this measure is reasonable to use. A very similar technique can be used to change the root mean squared error into the root mean squared scaled error. So also the scaling factor is different. For interval forecasts, the pinball function was introduced as a measure in the GEFCON competition. As you have seen, it's a measure which penalizes for being above or below a given quantile, not exactly hitting it. The interval, also called the Winkler score, is an alternative where it also penalizes for the width of the interval. So it gives you kind of two in one. You have penalized from the width and penalized for deviations from this or lying outside the interval. For density intervals, there's a technique called continuous rank probability score. A good reference is this paper here. Now, once we have the forecast, we can compare them between themselves. I mean, you see one method yields larger error, one yields smaller errors, but can we say that one method is significantly better than the other? And to do this, and this is something which has been essentially neglected in the vast majority of papers, we are not testing for the significance. We're just showing that this method is better than the other. So this can be done, for instance, using the most common test, the Diebold-Mariano test. It's just the significance between the difference of two forecasting methods. There's a very good recent article by Diebold where he talks about the use and abuses of this technique. Some alternative approaches could be the model confidence set, which is pretty similar, but uses a bootstrap technique to obtain the statistics. Forecast encompassing of Harvey, where you are looking at two models and asking a question whether the predictions from one model contain any additional information compared to the other. So these are techniques known in econometrics. They have not really entered, apart from one paper, I think, have not entered the energy economics literature, but this is something that I think is important to be considered in the near future, whenever we want to look at the significance of our results, not just whether we are better or worse, but whether this is significantly better. It's not just the randomness of our sample that we took. For probabilistic forecasts, that's the most common test would be the Christopherson test that we have seen used before in the slides. Some extensions and alternatives are discussed, for instance, in the paper of Berkowitz and others from 2011. If we are talking about density forecast, probably the most well-known technique is the density evaluation technique of Berkowitz, which is popular pretty much in the value of this literature. So summing up, I have discussed today 5 major areas which will or should be developed in the near future in the context of modeling or forecasting load prices. Loads. These are techniques which are recently either gaining on popularity or still not very popular, but in my opinion, they should be introduced into this literature, as they can allow for a better comparison of the different techniques published or different techniques used by different companies. As a final slide, I have an invitation to a session I'm organizing during the Modern Electric Power Systems Conference in Wrocław in 2 weeks' time. There will be an energy economics and forecasting session. More info is on the webpage. You can Google it. If you are interested, you are very welcome to attend this event. It's on Monday, Tuesday, July 6th and 7th. Thank you very much.
Okay, any question?
Yes, my first question is about the methodology you have presented on the combination of predictors. Mm-hmm. So you have presented 3 models based on this methodology, mm-hmm. the naive one, and 2 other. Could you describe how you compute the weights for the 2 other models, or giving the idea how to compute the weights?
Mm-hmm. You mean like this model?
Yes.
And, it's all the same. It's all quantum regression. It's mm-hmm. just standard quantum regression technique. Yeah. It's implemented in many software programs. For instance, yeah. I mean, we've been using MATLAB implementation, yeah. but you can find it in R in different other statistical environments. It's just a way of minimizing this function. So essentially, this is minimizing just this yeah. function. That's it. It's a numerical technique. Okay. Yeah, I don't know, from the 80s to 80s or something. Yeah, it's relatively simple. It's just the different inputs are to this method. Okay. That's the difference.
But is it possible to explain, for example, because I don't know the literature, but maybe in the literature some people use neural network to estimate, but in a more complex one.
Well, these individual point forecasts yeah. can be from any technique. They yeah. can be even experts. You can ask an expert, and one expert will say, okay, the tomorrow's price will be 200 euros. The next expert will say use 50 euros. You can combine those. You can get those forecasts from a neural network.
Okay.
Anything. This is a very general technique which just uses point forecasts of different forecasters. Whatever a forecaster is, this can be a technique, this can be a person. this can be a different data set events, like in the sister forecast approach, you have the same general model, but you use different calibration data sets to obtain slightly different forecasts. So all these methods use some forecasts, then apply quantitative regression. Yeah. The one with when you have this factor quantitative regression is a bit different because you first extract the principal components, yeah, out of this large data set. Okay? If you have like 6, 8, 10 predictors, doesn't make sense to use it. But if you have above 20, 30, then it may make sense to extract first and then combine them again using the same technique, quantitative regression. This is kind of standard.
A couple of questions. You basically distinguished point estimation with respect to probabilistic estimation. I mean, in practice, point estimation is a way to estimate some source of trend, whereas probabilistic is to estimate a probability distribution, right? So what you call probabilistic estimation is it's the same as the statistical estimation of stochastic processes, which basically dates back to the 70s for continuous time processes, possibly continuous as well as discontinuous processes, with either continuous observation or with finite sample data, as the Danish school developed in the early of 2000. So that's my first question. Is that what you mean with probabilistic estimation? Estimating a stochastic process under the historical probability as opposed to calibrating to price?
No, probabilistic forecasts. Okay, this is not the term I have really came up with. It's been there. I mean, some engineers were also using it, but they also find it in some econometrics papers. It's just a way of not forecasting the mean value, the future mean value, because a point forecast is the mean value, but forecasting certain quantiles. This can be, like, say, the 5% quantile, the 95% quantile, but this can be a whole range of quantiles. If you take all the percentages from 1 to 99, so 1, 2, 3, or 4% to 99%, you essentially have the whole distribution covered. So it's just a way, in the simplest comparison would be like a comparison between the mean and the median, right? The 50% quantile is the median. So they give you slightly different information.
It's like a non-parametric estimation of a statistical
you can't. Okay, yeah. I'm not saying that this is completely new idea. It's maybe the application to electricity market is new. Some techniques are new. But the general idea of obtaining the quantiles of the future value of the process is not new, definitely. Okay.
The second question is, when you deal with point estimation, you focus on average values. And now you add this idea of probabilistic estimation focusing on quantile. But what about applying the same methodologies you have presented for the estimation of the pattern of some either statistics or parameter of the underlying distribution? For example, volatility. One may find seasonalities in particular, or more in general, periodical patterns at varying frequencies, not only in the trend, but also in the volatility.
Yeah,
so you can apply the
techniques is very general. So it's going to be applied to any process. This can be the price process. This can be the volatility of this price. There's no restriction here. So the technique is just a numerical technique or statistical technique.
Okay, but has it been applied?
To my knowledge, in electricity, in energy economics, not really. But if you think about value at risk, this is what people have been doing since the 1990s at least. It's essentially estimate the quantiles of a distribution of the profit and loss distribution. Okay? Not necessarily volatility, but okay, some applications can be in this direction also. So you can think of whenever you are interested in the distribution of a process in the future, you can use this technique to obtain the estimates of the quantities of this. It's a general technique. It's not related to the levels. It can be any process essentially.
Okay, and so there is actually another set of methodologies that has been applied to price estimation since the time of Mandelbrot, the fractal methodologies. Have they been applied to electricity in light of kind of similarities varying the granularity of data?
As far as I recall, there are a few papers where this kind of techniques are applied. For instance, if you think about forecasting, this will be typically in the discrete time domain. So you would look at, for instance, ARIMA processes. So ARIMA with fractional integration, and this kind of corresponds to what we're talking about, so similar processes. Just one or two papers that have been written on this. The technique is much more complex. Estimation is more complicated. The results are not much better, so it doesn't lead to big profits in the end.
Okay, thank you. Any other question?
Additional question, please. So as far as this slide is concerned, so then basically you are underscoring that you have point forecast. So for each of them you don't have standard errors, right? Because you just have point forecast.
Yeah.
So have you thought maybe to apply like bootstrapping, like alternative percentile bootstrapping, to basically take into account that you are estimating, say, n models, but you have a standard errors coming from the fact that these are all different, you know, and then you just estimate it linearly for the quantile regression. So I don't know whether you thought about this.
We are working on this right now, a different look at this. This was kind of a first try, and it turned out in practice, it turned out very good. But yes, now we are developing it and looking at combining not necessarily a point forecast, but also interval forecasts or density forecast. So in this respect, yes, there's more to be done differently in this area, but it's not straightforward, not just a straightforward weighting of the interval of the quantiles. Something more has to be done, and I think there is potential in this. So it seems that this probabilistic forecasting, or maybe the more traditional name would be interval or density forecasting, is a new line of research that is really developing rapidly now, and this is of practical use. So I think a lot of effort will be put into developing new techniques that will allow you to get better and better interval or density forecasts.
Okay. Thank you.